Strange atmosphere is, in effect, turned off and on by the sun.
This is a little bit like what the atmosphere of Pluto might be like when Pluto is closest to the sun. And then as the sun goes away from Pluto, this is what happens. We're going to stick this balloon into this really cold liquid, and the balloon starts to collapse and shrink and get smaller and smaller and smaller as the pressure of the gas inside goes away. And hold it here long enough, and now I have a totally collapsed balloon. Now you'll notice as I pull it back out, it's starting to warm up again. There's actually liquid air inside there, and the gas starts to expand and swell up. And this is kind of what happens with Pluto's atmosphere, we think, over the course of its year. At perihelion, or when it's closest to the sun, you have this big atmosphere, and then when it gets furthest away from the sun, the atmosphere shrinks and could maybe even disappear entirely.
No other known body has such a radically fluctuating atmosphere. And the more scientists study it, the stranger it becomes. Fran Bagenal, professor of astrophysical and planetary sciences at the University of Colorado, thinks that Pluto looks like a comet because it has an atmosphere that leaks into space. Pluto's gravity is so weak that its atmosphere stretches hundreds of miles above the surface.
Similarities with the comet are that the weak gravity of Pluto allow the atmospheric gases to escape. And so, as Pluto gets closer to the sun, you have greater evaporation and more material escapes. Indeed, it looks very much like a comet in that respect.
When a comet travels towards the sun's heat starts to affect its icy surface. Ices turn into gases and are blasted away, giving the comet its distinctive tail of ionized gas and dust. Although Pluto doesn't release dust like a comet, it does leak up to half a ton of atmospheric gases every second. And this leads scientists to a startling conclusion. Pluto must be shrinking. Each time it heats up, it gets a little smaller. During our solar system's lifetime, as much as 18 miles of Pluto's terrain may have been lost to space.
And so as a result of this, we expect there to be a considerable variation in the surface, hills and valleys that have evolved over the age of the planet.
Hidden for decades, Pluto's strange surface is obscured to even the most powerful telescopes. But there is a special type of device that can bring it into focus. The infrared spectrometer reads the distinctive reflective signature of Pluto's surface. Using this technology, scientists can piece together a remarkable picture of the strange world of Pluto. Spectrometers tell us that Pluto's surface is covered by exotic ices. Temperatures on Pluto drop to a chilling -396 degrees Fahrenheit, so that nitrogen, methane, and carbon monoxide exist as frozen solids. The gases we breathe, see through, and move through on Earth make up Pluto's rocks, plains, and hills. Astronomers think that around 30% of Pluto is made up of ices. Beneath the exotic ice-covered surface sits a water-ice mantle. But is Pluto just a frozen world? As scientists investigate this puzzling dwarf planet, an intriguing possibility emerges. Could there be an ocean hidden beneath its surface? Could the existence of ice and liquid water on Pluto provide further evidence that the Kuiper Belt was a source of Earth's water? Scientists believe that Pluto-like worlds may have played a fundamental role in bringing water, the vital ingredient for life, to Earth. In the outer solar system where the sun's influence is weak, water ice is abundant. But could Pluto also have liquid water? Professor Bill McKinnon of the Washington University in St. Louis thinks so. He believes that beneath Pluto's frozen surface, there could be an ocean. McKinnon believes that water on Pluto could exist in liquid form due to the presence of ammonia, which acts like antifreeze. If he's right, water could remain liquid at temperatures far lower than those of the Antarctic.
Bodies like Pluto can actually have oceans. Not oceans on the surface like on the Earth, but oceans down below. And I have basically Pluto right here in this glass, and I can add the water and something like ammonia that would be inside Pluto.
Add ammonia to water, and the freezing point plummets to nearly minus 142 degrees Fahrenheit.
And to make it look more oceany, although we have no idea what the color of Pluto's ocean would be, we'll add some food coloring. Now out there in space, you're a long way from the sun, so it's cold. And so the top will freeze, like on a lake or in the Arctic, and you'll actually start freezing from the top down, and you'll make a thicker and thicker layer of ice, and I'll start it off by adding some ice at the top, which will float. And then, because we can't actually go into deep space, we'll put it in the freezer. But I put an earlier version of this a couple of hours ago, and this is sort of what you'd actually get. You'd actually see an icy layer floating on, I can jiggle it a little bit, a liquid layer that actually won't freeze.
After 2 hours in the freezer, the ammonia keeps the water liquid. But turn the temperature down below minus 142 degrees, and even ammonia-rich water freezes. On Pluto, surface temperatures are a mind-numbing minus 390 degrees Fahrenheit. At temperatures this low, every drop of water should freeze. So for water to remain liquid under the surface, there must be another force at play. A force that scientists believe lies deep inside Pluto's inner rocky core. Here there may be radioactive substances which generate heat as they decay. This heat could raise Pluto's subsurface temperatures to the critical level where ammonia-rich water can exist. It's a tantalizing theory. Because whether in liquid or frozen form, the presence of water on Pluto and its Kuiper Belt neighbors could hold the key to one of our planet's greatest mysteries: the origin of its oceans. One popular theory suggests that comets, which are rich in water ice, may have delivered water to Earth. But Dave Jewett thinks comets may not be the only source of Earth's oceans. Jewett believes Pluto-like bodies in the Kuiper Belt may also have played a part. It would take roughly 1 billion average-sized comets to deliver Earth's water, or one single ice ball 600 miles across. No comet this large has ever been discovered. But in the Kuiper Belt, there are between 50 to 100,000 ice-rich objects larger than 60 miles in diameter, and dozens at least 600 miles across. At the dawn of the solar system, astronomers estimate that the Kuiper Belt was around 100 times more massive than it is today. Sometime in the past 4 billion years, the Kuiper Belt has shrunk.
Several tens of Earth masses, even up to 100 Earth masses of stuff, originally was present in the Kuiper Belt and then was lost by some process that remains mysterious.
Could this loss coincide with the creation of oceans on Earth? This is Neptune, the 8th planet and the Kuiper Belt's closest gas giant. Computer simulations show Neptune's huge gravitational field may have dislodged Kuiper Belt objects, sending them spiraling toward the Sun. Parts of them may have collided with Earth.
We know there was a period of time when there was just stuff slamming in all over the place. And that had to hit the Earth too. It's possible, entirely possible, that those objects were Kuiper Belt objects, which are full of ice and water. Most of the water is hanging out in the outer solar system, and all the rocks are in the inner solar system, but maybe by these stirring events, you can kind of bring these two areas together.
If the theory is correct, objects like Pluto in the Kuiper Belt played a part in delivering Earth's water, vital to all life as we know it. Pluto is slowly yielding its secrets, shedding new light on our solar system. But incredibly, almost 80 years after its discovery, we still don't really know what Pluto looks like. Despite powerful modern telescopes, there are no detailed images of Pluto. These, taken in 1994, are the clearest to date. They were captured by Hubble, the space telescope that escapes the distorting interference of Earth's atmosphere. The largest point of light in the center is Pluto. Its largest moon, Charon, is next to it. To construct a global map of Pluto's surface, Mark Buey turns to Hubble's infrared images.
Each one of these images represents one picture taken with the Hubble Space Telescope. You stitch all those pictures together into a uniform map, which then I can manipulate and make it look like a globe.
This composite globe shows a reddish surface with patches of light and dark, evidence that Pluto has a varied landscape. At the solar system's outer limits, beyond the reach of even the most powerful telescope, Pluto remains shrouded in mystery, but not for much longer.
You either need a bigger telescope or you gotta go there. And so, we're going there.
Right now, a sophisticated spacecraft is racing towards Pluto at around 1 million miles a day. It's ETA 2015. January 19th, 2006. The Atlas V rocket blasts off from Cape Canaveral, Florida. On board, the New Horizons spacecraft. It's on a 9-year journey to Pluto and the Kuiper Belt. This is a voyage into the unknown. Since NASA's inception in 1958, its missions have provided stunning pictures and vital scientific information about our solar system. Some have even involved robotic landing vehicles to examine and explore these new worlds up close. NASA has sent spacecraft to every major body in the solar system, except Pluto. Pluto is still waiting to be explored. In the first ever image of Pluto taken almost 80 years ago, the planet appears as a tiny pinprick of light, no brighter than a distant star. Even the latest images, captured by the Hubble Space Telescope, show Pluto as just a blurred ball of light.
Pluto is so far away and so small that Hubble's capacity to see detail is greatly limited.
To get a sense of what it's like to try and see Pluto, best thing to do is to think about if you were to look at a ping pong ball, someone was to carry it 25 miles away.
An important clue to Pluto's appearance comes from data gathered by another mission to the outer solar system. In 1989, NASA's Voyager 2 skimmed past one of Neptune's 13 moons, the mysterious Triton. This flyby provided astronomers with a tantalizing glimpse of what Pluto might look like.
This icy moon, this large icy moon, that's very much a companion to Pluto, similar size, similar part of the solar system, and maybe had a very similar origin.
Astronomers theorize that many billions of years ago, Neptune slung Pluto outwards and dragged Triton towards it, taking it captive as a moon.
Triton is just like Pluto, but it got captured by Neptune billions of years ago. If we were to fly over Pluto, we would see impact craters and volcanic calderas or collapsed craters, and maybe even active venting or plumes, because we see these things on Triton.
Triton's strange landscape suggests that Pluto could be a dramatic place. And on Triton, the most dramatic features of all are geysers. Voyager 2 captured these remarkable images, evidence of geysers that last for up to a year and spurt gas and dust up to 5 miles high. If there are similar geysers on Pluto, astronomers predict that they would be driven by the sun. Although the sun is over 3.5 billion miles away, its heat may still have the power to affect the ice beneath Pluto's surface, turning it into gas. Pockets of subsurface gas would build up and eventually burst through Pluto's frozen surface as geysers. Will Grundy demonstrates how even a small increase in temperature produces a large geyser.
Okay, we're going to put liquid nitrogen into this plastic bottle, and it's very cold at 77 degrees above absolute zero. So as soon as it comes into contact with the hot environment here, with the sun shining and the warm air, it starts boiling like crazy. And as it boils, it's going up into gas, giving off a huge amount of gas. And as soon as I screw the lid on, the gas has nowhere to go except up the tube in the lid and out through this cooler full of ice to form our simulated geyser. And here it comes. On the surface of Pluto, don't know what the scale of those geysers would be, whether they'd be very small like this one or maybe a kilometer tall.
Such mysteries will be solved on New Horizons' arrival in 2015. The spacecraft's camera has already been tested 6 months into its epic journey, capturing perhaps the greatest volcanic eruption ever witnessed in space. 76 years after Pluto's discovery, and after 17 years of research and development, NASA's New Horizons spacecraft sets out for Pluto. Traveling at around 1 million miles a day, it's on a 9-year, $700 million journey to reach Pluto and reveal its secrets. New Horizons chief scientist is Hal Weaver.
Yeah, where we are right now is mission control for the New Horizons mission to Pluto. This is where we watch all of the activities that are occurring on the New Horizons mission. We have over here to the left a depiction, a software prediction of exactly where the spacecraft is, where it's pointed. You know, we're following us on its path to Pluto.
In early 2007, New Horizons passes Jupiter, using the planet's intense gravity to boost it toward Pluto. It took the opportunity to test its camera on Jupiter's largest satellite, Io. The results were spectacular. This footage, captured by New Horizons' long-range reconnaissance imager, shows the actual eruption of a volcano on Io's surface.
We were just lucky and happened to catch it when one of the major volcanoes was active. It had spectacular plumes, debris, volcanic debris was flying up for a couple of 100 miles above the surface.
It's a stunning but short-lived encounter. New Horizons soon leaves Jupiter behind. Traveling at over 8.5 miles a second, it's the fastest spacecraft ever launched. It's going so fast that after its 9-year journey, New Horizons will only have a day and a half to see Pluto close up before disappearing deeper into the Kuiper Belt.
And that's great for getting there early. But on the other hand, of course, that means that everything is really sped up as we fly by, because unfortunately, we can't just go to Pluto, put on the brakes and stop and hang around for a while. roughly 3 months out, we're going to have resolution that's better than Hubble, and then it just gets better and better and better as we get closer and closer. But for those last 24 hours where we have this really high spatial resolution where we can see football field-sized features on the surface of Pluto, that all happens very quickly. We're just going to fly by and then just by Pluto and on deeper into the Kuiper Belt.
With such a short window to capture data, the team must test and retest the instruments throughout New Horizons' 9-year journey.
Every year, for about 2 months, we're going to wake the spacecraft up and do some testing. Some observations of celestial objects and some commissioning testing of all the instruments to check them out, to make sure they're still performing and they'll be ready to go when we finally get to Pluto in July of 2015.
Ready to answer some of science's most fundamental questions.
The delivery of organic material and water from the outer solar system to the inner solar system may have played a pivotal role in the formation of life on the Earth.
It's just one of many questions about the solar system and its formation that scientists hope New Horizons will help answer. But above all, when New Horizons arrives, astronomers are expecting the unexpected.
I think the most exciting things that we're going to learn from New Horizons are all those things that it never even occurred to us to ask. And suddenly you go there and you realize, wow, we didn't know anything.
One thing is certain. The arrival of New Horizons will be the astronomical event of the 21st century.
It's a whole new kind of world. It's a planet I think everyone has tried to imagine. It's a frontier world. It's going to be the cover of the Rolling Stone.
And perhaps most fittingly, the spacecraft carries the ashes of the man who started the journey to Pluto almost 80 years ago, Clyde Tombaugh. This is a journey to one of the solar system's most puzzling, most mystifying worlds. Once the 9th planet, now a dwarf planet, an isolated oddity that became one of many. A frozen wasteland that could be home to giant geysers and underground oceans, and even possibly to primitive life. With so many twists to Pluto's story, who knows what surprises lie waiting to be discovered? Waiting for New Horizons' arrival in July 2015. In the empty blackness of space, surrounded by hostile planets and freezing vacuum, planet Earth is an oasis of life. And all because of our protective cocoon of gas. This blanket of air shapes everything we see on Earth. It protects, insulates, and sustains us. It carries water around the globe and shields us from cosmic impacts and killer radiation. It's time to uncover the invisible wonder that is our atmosphere. Down here on the Earth, we rarely give much thought to our atmosphere. Because we can't see, smell, taste, or hear it, we take it for granted. But our air is all that stands between us and the vacuum of space.
We've got this canopy that provides us a lot more than just an atmosphere to breathe in. It definitely shields us.
The atmosphere is divided into 5 distinctive layers: the troposphere, stratosphere, mesosphere, thermosphere, and exosphere. Each layer is less dense than the one below, stretching miles above our heads.
How far out it goes is depending on which scientist you talk to. Some say it ends at 300 miles, some say it extends out to Mars.
We live in the layer closest to the ground. Here in the troposphere, the air is thickest and the pressure greatest. Our bodies are perfectly matched to these conditions.
Our chemistry, our very nature, our metabolism is completely shaped by the atmosphere.
To appreciate our atmosphere, we'll rise through its layers, traveling from the planet's surface, miles up above the mountains and the clouds, to the very edge of space. August 16th, 1960. one man is preparing for a record-breaking journey into the mysterious skies above. To a lethal world above 99% of the Earth's air, where an unprotected human would die in seconds. Where the temperatures plunge to 67 below, and the air pressure is 1/100th of that at the surface. Colonel Joseph Kittinger will travel almost 20 miles high. And then he will jump. This is a key military mission, one of the first steps in the space race. Kittinger will be testing the human body's resistance to high altitude, low pressure, and rapid free fall. He will be trialing new technology he hopes will protect him.
It had never been done before, but we were not there to set a record. We were there to gather information that we needed for our space program and for our high-flying aviators.
Ground crew prepares his vehicle, a helium balloon, and a rudimentary open-sided gondola.
Just an open gondola. It was designed just to carry me up there. It was a space platform, an elevator, I called it.
At 5:30, Kittinger's preparations are over. He boards the gondola.
My crew chief said, "Are you ready?" I said, "I'm ready, let's go." It was a very smooth takeoff, and I started ascending. Up, up, up.
30 minutes after takeoff, Kittinger reaches 29,000 feet, the middle of the troposphere. At this altitude, the air is so thin that each breath contains only 1/3 of the oxygen found at sea level. Kittinger breathes from gas bottles connected to his sealed helmet. He's still barely 1/3 of the way to the jump point. There are another 14 miles to go, and the air pressure is dropping rapidly.
So at about 40,000 feet, suddenly the pressure suit starts inflating, and that's when you start checking it to make certain that it's working properly.
But there is a crucial fault in the suit. The glove covering his right hand is not sealed.
I had an option to tell the ground that I had the problem, and I knew that if I did, they'd probably make me abort the flight. And I was concerned that if we had to abort that flight, that we would have been turned down to try to do it again. So I didn't tell them.
Kittinger prays that this is an isolated fault and continues to climb at 1,000 feet per minute. After 89 minutes, he approaches his target altitude. The balloon's climb slows and then stalls. Kittinger is in the mid-stratosphere, a record 102,800 feet high. And it is now time to make the long, swift journey down.
When it came time for me to jump, I was ready to jump because I was heading back toward a more friendly environment, a friendly planet that we're used to. I had made this jump 1,000 times in my mind. I'd gone through every step 1,000 times. Well, just before I jumped, I said a silent prayer. I reached over and hit a button that started the cameras going. And then I just did a little hop off the step of the gondola. You can't tell that you're going fast, you can't tell anything. And I looked up at the balloon, and the balloon was firing into space. And I said, gosh, that's amazing. And then I realized it was me that was going down at a fantastic rate, and the balloon was standing still.
He falls for 16 miles. The thin air offers almost no resistance. He reaches 614 miles an hour, approaching the speed of sound. After a record-breaking 4 minutes and 36 seconds of freefall, Kittinger opens the main parachute. He drifts down to the desert floor and lands.
We were just elated because we had accomplished what we set out to do. There was a lot of people who said we couldn't do it, and we proved that we could do it.
The mission has been a stunning success. Kittinger's skydiving record stands to this day. he takes his first deep breath of air with a newfound appreciation for our atmosphere.
It was a relief to be back on the planet Earth that we love so much. A planet that has an atmosphere that we can live daily.
Kittinger forged a dizzying path through the atmosphere. Our journey begins just a few feet off the ground with the air we breathe. We take for granted Earth's blend of gases, the perfect mix for heat and energy. And astronomer David Grinspoon believes we'd be hard-pressed to find its equal anywhere.
The more we learn about planets, the more we learn that they're all individuals. They're like people in that sense. So as far as what we know now, Earth's atmosphere is completely unique.
In the past century, telescopes and space probes have uncovered the extreme atmospheres of our neighboring planets. A journey across our solar system reveals exactly how unusual Earth is. Clouds of near-frozen gas flow over the icy surfaces of Uranus and Neptune, while the Sun has blasted away the atmospheres of Mars and Mercury.
To me, it seems as though Mercury doesn't have an atmosphere at all. In fact, if you were on the surface of Mercury, it would look to you as if you were out in outer space.
In contrast, Jupiter and Saturn are all atmosphere.
Unlike Earth, Jupiter doesn't really have a solid surface that you could stand on and then have your head up in the atmosphere looking at the clouds. It's just a giant, giant gas ball.
Only one other planet shares the Earth's thick atmosphere and rocky surface: our near neighbor, Venus. But even here, there are striking differences. Dr. David Crisp has spent 20 years studying Venus's acrid air.
Imagine you're at the surface of the planet Venus. You're at pressures that are high enough to crush a nuclear submarine. The pressures there are about 90 times the pressure of the Earth's surface.
This pressure is combined with extreme heat, 900 degrees Fahrenheit, hot enough to melt lead. Clouds drift over the baked surface, but they are not water vapor. Venus's clouds are made of concentrated sulfuric acid. Venus is a stark example of how extreme an atmosphere can be. But the real mystery isn't why Venus is so hostile, but why Earth hasn't followed the same path.
As planets go, Earth and Venus are essentially twins. They're almost exactly the same size. They're also very close together in the solar system. In spite of that, their environments evolved in dramatically different ways.
To discover why these twin planets followed separate paths, and to explore what gave us our precious atmosphere, we have to travel back 4.5 billion years, to the birth of the solar system itself. The birth of the solar system created Earth's earliest atmosphere. Huge quantities of material orbiting the Sun fused together into protoplanets. Jupiter and Saturn formed into gassy spheres. But on Earth, most of the material condensed into a molten core. The remaining gases bubbled forth from the liquid rock, forming the first atmosphere. Our planet's gravity stopped these gases from drifting off into space. But Earth now had to face the ravages of the solar wind, a stream of charged particles thrown out by the Sun. This same wind had a catastrophic effect on Mars. It has stripped the air from the planet's surface, blasting it deep into space. The red planet's atmosphere is now only 1/100th as thick as Earth's. Our planet was spared this fate. The magnetic field generated by the Earth's core blocked the solar wind, preventing it from blasting away the fragile air. But the Earth's atmosphere was still very different from the one we breathe today. It contained high levels of carbon dioxide, a gas with a key ability to absorb and hold on to heat. Carbon dioxide still makes up 95% of Venus's atmosphere. It superheated our twin planet to the point where its water boiled away into space. And yet, this didn't happen on Earth. David Crisp believes that was down to a chance event.
If Earth kept all of its initial atmosphere, it probably would have turned out a lot more like Venus. But that didn't happen. We were the victims of a very lucky accident.
Earth's big break came 4.5 billion years ago. Back then, the solar system wasn't limited to the 8 planets it has today. Instead, a swarm of protoplanets, or planetesimals, orbited the sun like bees around a honeypot. One Mars-sized body was heading straight for Earth. In a colossal cosmic collision, it slammed into our planet, creating our moon, and according to Crisp, removing the atmosphere that still blights Venus. This ancient event was the defining moment for our atmosphere. With the original deadly gas mix blasted away, our planet's air could slowly evolve into what it is today.
We were left with this atmosphere made of molten rock and vaporous rock. It took millions of years for that atmosphere to fall out and to be replaced by an atmosphere made up of nitrogen and carbon dioxide and water vapor.
These new gases came from above and below. Volcanic eruptions spewed out fresh stalks of nitrogen and carbon dioxide from within the planet's molten core. While the vital element of water may have been delivered by icy comets, each impact bringing a new supply of frozen liquid. But the air still lacked one of its key ingredients.
One of the things that was missing is free oxygen, molecular oxygen, O2, the stuff we breathe.
Dr. Janet Seifert of Rice University in Texas searches for the event that produced the atmosphere's final element.
We know from the rock record that for the first half of Earth's life, there was no oxygen in the atmosphere whatsoever. There were greenhouse gases like methane and CO2, but there was no oxygen.
But the rock record shows a sudden change, dated to around 2.5 billion years ago. Evidence of the first oxygen in the atmosphere. The gas was released by a humble microscopic living organism called cyanobacteria.
Well, it turns out cyanobacteria are the only things that can actually produce oxygen. So we know that at some point cyanobacteria colonized enough of the planet in order to produce enough oxygen that it became resident in the atmosphere.
As the microbes multiplied and spread, the gas built up in the air, transforming the planet in a process known as the Great Oxidation Event.
Oxygen is very powerful. The world gets turned upside down. Everything has to begin to adapt to now a completely new atmosphere where oxygen is dominating.
First, the oxygen reacted with the oceans, causing iron within them to form rusty deposits on the sea floor. Then its effects reached dry land. It reacted with soil and rock, giving them a reddish, rusty tinge. And once these minerals had absorbed their fill of oxygen, the gas began to gather in the atmosphere, with dramatic consequences for life.
Complex animals could have much higher metabolisms because of the sheer potential that oxygen provided for them, and a whole different kind of evolution was able to take place.
Powered by oxygen, life evolved from single-celled organisms to complex animals. And plants also began releasing oxygen, thanks to an ancient adoption of photosynthesis.
A very ancestral, primitive plant cell either engulfed or tried to digest or surrounded a cyanobacterium. And instead of digesting it, it actually became an organ within the plant. So every bit of the oxygen, even if it's coming from a plant that you see in your yard, is coming from an ancestor of a cyanobacteria resident inside the plant.
With the rise of oxygen, the air's unique blend of gases was complete. This air we breathe has changed planet Earth, molding its terrain and habitats. And as we continue our upward journey, we run into another vital substance: water. The turbulent movement of our atmosphere carries water vapor around the globe. Powerful winds and violent storms smash our buildings and drown our fields. But without them, the land would be bone dry. Our atmosphere is in constant motion. The moving air that causes our weather circulates between the ground and 50,000 feet. It is the sun that drives this movement. When solar energy reaches Earth, it heats the surface and atmosphere, but it does so unevenly. This temperature difference causes the air to move. Hot air near the equator expands and rises. Cold air at the poles becomes denser and sinks. NOAA's Marty Ralph can track its movement over the globe on the revolutionary Science on a Sphere simulator.
What we're seeing here is a portrayal of the Earth's surface temperature, and red and warm colors are warm temperatures like we see in the tropics here. Up in the poles, you see the blues and the greens. Those are the colder surface temperatures. So we can watch this and actually see the warm air moving northward, the cold air moving southward, and we can see the changes in the seasons.
If the atmosphere didn't move, the poles would be 45 degrees cooler and the equator 25 degrees warmer. The great deserts of the Sahara, Atacama, and Mojave would expand dramatically. Northerly cities like London or Boston would be locked in an icy winter. It is only the atmosphere's circulation that prevents this. It regulates the temperature, moving the air to create the weather that covers our globe. The planet's rotation twists the air as it flows, helping form the hurricanes that lash the coasts. As moist air wells upwards, clouds become electrically charged and send lightning bolts crashing down to Earth, superheating the air to 18,000 degrees. And as the air cools, water vapor condenses into clouds and rain. This water evaporates from the world's oceans. At any moment, 0.001% of the world's water is being carried in the air. But that tiny percentage adds up to almost 3,000 cubic miles of liquid. If the air didn't carry water, the land would be bone dry.
Storms do a really important job for the atmosphere. They help reduce the difference in temperature between the poles and the equators. And in the process, they actually create the rain and snow that we depend on.
One of the most powerful weather systems is a newly discovered set of water channels running through the air. Ralph's current research focuses on these mysterious rivers in the sky.
One of the phenomena that really influences where the water is available for us are these regions where water vapor transport is focused. We've come to recognize that phenomena as an atmospheric river.
Atmospheric rivers are narrow channels of hurricane-force winds that can stretch for thousands of miles. A single river can carry 3 times as much water as the entire Mississippi. They provide almost half the annual rainfall for parts of the American Pacific coast, but when they remain over one area for a day or more, they can produce violent flooding.
Heavy winds, lots of water vapor, a storm track that's not moving fast adds up to a big flood event.
The rivers were only recently discovered because they form over the world's oceans. We still don't have enough data to forecast their floods.
An example of the challenges we face in weather prediction is that while this model can actually produce an atmospheric river, like we're seeing right here, a week ago today we looked at the forecast for today, and it said there should be a strong atmospheric river creating heavy rain in Northern California. Well, instead, it's hitting Canada. That's a huge difference.
To fill the gap in data, Ralph explores the rivers on research flights. The rivers form in front of banks of cold air. They create channels of wind that carry huge quantities of water vapor from the ocean to the coast at up to 100 miles an hour.
These are like conveyor belts for water vapor. They're very narrow, and yet they do 90% of the water vapor transport for the global atmosphere at those latitudes.
When the airflow hits a mountain, it rises up, shedding its water as rain and snow. Ralph has tracked how the rivers move with the changing seasons. But to fully forecast the floods, he needs a lot more atmospheric data. He believes robotic drone aircraft, developed for the military, could continually measure the air over the oceans, charting its temperature, winds, and humidity. And the flights could also track how the rivers are changing.
We're starting to see evidence that the more intense atmospheric rivers might become more frequent in certain parts of the world, and that will contribute to increasing the frequency of flooding.
The changes Ralph has identified are part of a wholesale shift in our climate and atmosphere. Deserts are expanding, while rainforests are drying out, all due to a change in the chemical makeup of the air. This blend has always been in flux. We alter the proportions with each breath we take, but our factories and homes, planes and cars amplify the process. For over 2 centuries, we have been dramatically increasing the amount of warming carbon dioxide in the atmosphere. So far, the planet's natural air filters have pulled nearly 55% of it out of the air.
The North Atlantic has absorbed a tremendous amount of carbon dioxide, but at the moment it's almost completely saturated by carbon dioxide, so it's not absorbing very much more. It's almost like a bottle of some kind of soda pop. If you warm it up a little bit, it'll actually fizz and release CO2.
As these natural safety valves close, we will face an even more dramatic rise in temperatures. The global average could be up 7 degrees Fahrenheit by the end of the century, wreaking havoc with weather patterns and habitats. We can prevent climate change by preserving the air's delicate blend of gases, the unique mix that sets Earth apart. And our planet is also marked by how this blend sits above the surface in a distinct layered structure. As we rise above the clouds and winds of lower altitudes, we enter a completely new zone. A world of extreme temperatures and ever-thinning air. Air that would kill us in seconds, but which shields us from deadly radiation. We live in a tiny sliver of Earth's atmosphere called the troposphere. Winds and clouds, rain and snow dominate this turbulent zone, but above it lie miles of freezing dry air. The conditions there would kill a human in seconds, but we desperately need the high atmosphere's weight and protection. Engineer John Powell's balloon team has spent 27 years exploring its layers, pushing further and further into this remote, dangerous world.
Sometimes we just run into a phenomenon that we have no idea what that was. We just have this moment of data in it that we need to go back and explore. But it really is like a completely alien, foreign world up there.
The team has made over 90 launches. Each one edges them closer to their ultimate goal of reaching space.
You can use balloons not just to go to the edge of space like we do now, but go all the way over the line and actually use balloons or airships to go all the way into space. Space travel without the rocket.
Officially, the atmosphere ends and space begins 62 miles up. This sounds high, but on a tabletop globe, that would only be as thick as the coat of varnish. And in reality, the air extends out much farther. The atmosphere's lowest layer, the troposphere we live in, ends 40,000 feet up, the cruising altitude of airliners. Above are another 4 distinct layers.
They're all separated by their temperature. It gets colder and colder and colder, then it warms up to a nice toasty 0, and then it starts to get colder again. So whenever the temperature changes directions, you know you've made it into another layer.
First comes the stratosphere, a stable layer without strong winds. Then temperatures in the mesosphere plunge to minus 150 degrees Fahrenheit. Above that is the thermosphere, where solar radiation can push the thermometer back up to 4,500 degrees. And finally there is the exosphere, an endless zone where air molecules slowly thin out into the pure vacuum of space.
Now, the exosphere is really high. They actually detected particles of the Earth's atmosphere on the far side of the moon during the Apollo program.
As Powell's balloons rise towards space, they leave the world we know far behind. The air thins, and they begin to lose the protective weight of the miles of air above them.
The pressure is dropping. When you finally get to the stratosphere, to the altitude we like to work at, it's only 1/100th that of it is on the ground. It is a whole different world than down here.
The weight of the miles of air above us creates air pressure. We often think of air as weightless, but all those gas molecules add up. Grand Central Station's main concourse contains over 200 tons of air. As gravity pulls the air down, it compresses the layers below, making them denser. This dense air is what we are used to dealing with on the ground. Just a pint of it contains more than 8.5 billion trillion gas molecules. But higher up, around the balloon, there is less atmosphere pressing down from above. The air up here is thinner.
It's like being under 1,000 blankets, and each blanket is a layer of the atmosphere, and we're being pushed under all of these blankets. Now, as you go higher, you're going up through the blankets, so it's pushing on you less, until you're at the top, then above most of the blankets where you don't feel it at all.
That thin air seems alien to us because our bodies and technology are so perfectly adapted to thicker air. We even need it to hear. The gas carries sound through air as pulsing waves of pressure.
Sound is just a wave, like a water wave in a pond. But if you take away the water, there's nothing for the wave to go across. And as the atmosphere gets thinner and thinner, it supports that wave less and less and less.
Finally, in the vacuum of space, there is nothing to carry the wave. And even the largest explosion is silent. School science experiments on board the airship study the dramatic pressure change.
And we call it a PongSat, for ping pong ball satellite. And it's real simple. The first thing they do is they have to cut the ping pong ball in half. Then your experiment goes inside. And the simplest and my favorite is where you take like a little mini marshmallow and they just drop it in the ping pong ball. This is satellite construction at its best. And then we take them to the edge of space.
In the thin air of the stratosphere, the marshmallow is no longer held together by high air pressure. Air bubbles inside it expand, causing the spongy candy to bloat outwards and burst open the PongSat. Just as the thin air is dangerous for marshmallows, it can also affect flesh and blood. Contrary to popular belief, your blood won't boil. It's held in by your blood vessels. But any exposed flesh will swell out like the marshmallow. And at around 26,000 feet, the air is too thin to breathe. There just aren't enough molecules in every lungful of air. And starved of oxygen, your brain will begin to shut down.
You know, the extreme cold would get you, but the lack of pressure would get you first.
As the balloons rise higher still, they face attack by an invisible bombardment, radiation. Every day the sun radiates a titanic amount of energy, some of it in the form of high-energy ultraviolet rays. These rays pack a powerful punch, and in the high atmosphere, they attack the structure of Powell's balloons.
The UV literally damages the material, and you start getting microscopic cracks in the material, which makes it brittle. Eventually, it just fails, and the balloon pops.
The rays are potential killers, both for balloon and human. They bombard our cells and DNA, triggering cancers. But around 7 miles up, a layer in our atmosphere shields us from 99% of these rays. It is made up of ozone, a rare molecule of 3 bonded oxygen atoms. This can absorb and block high-energy UV rays.
The ozone layer, it's not like this saran wrap thick layer or boundary that you pass through. It's actually miles and miles thick, so it's a slow diminishment.
Man-made chemicals used in refrigerators and aerosols have been eating away at this delicate protective layer. Every winter, holes in the shield appear over the poles. The harmful chemicals are now banned, and the layer is beginning to recover. And above it, the fragile air of the mesosphere is shielding us from another deadly barrage from space. In East Texas, Jeff Notkin and Steve Arnold are searching for the remains of cosmic missiles that have been shattered by our atmosphere. Fragments rarer than diamonds and worth their weight in gold. Meteorites. These two professional hunters seek out space rocks buried in the fields and prairies.
This search for meteorites allows me the chance to touch a little bit of what's from out there, bits of the cosmos that have found their way to us.
The hunt has taken Steve and Jeff from Siberia clear down to Chile, and some of their finds have been spectacular.
The largest meteorite I found was 1,430 pounds. It was a large stony iron meteorite from up in Kansas. We didn't realize it was that big of a deal. The media kind of picked it up and ran with it.
He's very modest. It's not only Steve's greatest find, it's one of the greatest finds ever made in meteorites.
The massive space rock has been valued at up to a cool $1 million. But this is a rare find because most meteorites simply don't survive a brush with Earth's atmosphere.
Most of them don't make it to the surface. The atmosphere is our friend in the sense that it protects us from these rocks from space, but for meteorite hunters it's also not our greatest ally because it burns up a lot of what we're looking for.
Steve and Jeff search for remaining fragments using a custom-built metal detector rig.
Meteorites will have iron in them, and it's ferrous, and so not only will a magnet attract to it, but also a metal detector will be able to pick it up.
Every year, over 18,000 meteorites lock onto a collision course with Earth.
When meteorites encounter our atmosphere, they're traveling at the speed that they acquired while moving through the vacuum of space. And typically, they're traveling at many thousands of miles per hour.
As they head down to Earth, they cut through the outer reaches of our atmosphere. But once the meteorites enter the mesosphere, the air starts pushing back.
We can't see the air around us, and we can only feel it on really windy days like this. But a meteorite encountering our atmosphere definitely feels the air, and that is because it's traveling so quickly. When it encounters our atmosphere, the air in front of the meteorite cannot get out of the way in time. It's almost like the meteorite hitting a solid wall, like a block of concrete.
As the air in front of the meteor compresses, it also heats up to more than 30,000 degrees Fahrenheit. Eventually, it bursts into flame, lighting up the sky. When you see a falling meteorite or shooting star, it's actually the protective shield of air that you see burning, not the meteorite itself. But the friction and heat wears away at the space rock. The hot air actually melts the metal surface. And often the collision with the atmosphere can have a shattering effect, splitting the meteorites along fissures.
This is an actual meteorite, and if this were to encounter the atmosphere at high speed in its current condition, and that's the result.
Only fragments of the original asteroid survive the fall to Earth. Their speed has dropped from 17,000 to 300 miles an hour. Rocks as big as station wagons have shrunk to the size of golf balls. They impact on the surface, forming holes a few inches deep. The chances of finding one are remote.
There we go.
I'll get the shovel.
Right about there, Maestro.
It looks promising, but this time the guys are out of luck.
So yeah, we found a plow, and basically a lot of different types of trash can be in these fields, and so anything that's ferrous, our detector's going to pick up. Meteor wrongs, as we call it, as opposed to a meteorite.
On average, they uncover 75 meteor wrongs for every meteor right.
This is a genuine iron meteorite. This is believed to have once been part of the core of a long dead planet or asteroid. And this was found right here in this strewn field. These remarkable little shapes, indentations on the surface, are called thumbprints, or scientifically regmaglyphs. And that's a feature that's unique to meteorites. And these little markings are caused by the surface actually melting as it flew through the atmosphere. We don't find regmaglyphs on Earth rocks.
The air is constantly at work, making meteorites rare and valuable.
The chances of meteorites surviving their journey through the atmosphere and being found are minuscule. If it wasn't for our atmosphere, we would have little particles raining down on us all the time, and some of them not so little.
The mesosphere's barrier of thin air is the final gift from our atmosphere, adding to the oxygen we breathe, water we drink, and pressure we feel. But as we cross into the layers above, we leave life far behind. John Powell's airships have only reached the upper stratosphere. Kittinger's jump point is below that, in the middle of the stratosphere. The only people who travel through the superheated thermosphere and distant exosphere are astronauts heading for space. One day, these manned space missions may reach out even further, to distant planets with alien atmospheres. Atmospheres that may support their own life forms. Elsewhere in our universe, on distant planets, alien air may support extraterrestrial life. Joel Hagen has spent 20 years imagining how those atmospheres could have affected their inhabitants.
That's where some of the real creative joy comes from, is trying to think about everything that has happened here and then take yourself one notch beyond it and imagine, what haven't I seen yet? And then try to visualize that.
One of the possibilities that intrigues Hagen is life on a gas giant planet.
This is an environment so completely alien to what we're used to. Even a planet like Jupiter, for instance, has no solid surface, just a gradual transition of densities of gases. And I think we might imagine creatures in an atmosphere like that sort of relied on buoyancy, perhaps being able to generate hydrogen, for example, somehow within their bodies.
These creatures would be like hydrogen-filled blimps, lighter than the air, able to float amongst the gas clouds.
The concept that I have here is to have perhaps colonies of microbes in these sort of tentacle-like structures here. And these microbes generate the hydrogen, which in turn sort of inflates the gas bag here. A creature like this then could sort of float freely at certain levels in the atmosphere.
On other planets, with denser atmospheres, larger, more complex creatures could take to the skies. The thicker air would support them aloft, allowing bulky reptiles to glide and fly.
This creature probably wouldn't be able to fly very well on our planet, but even on a planet like Titan, for instance, it has a surface gravity only about 15% of Earth's, but an atmospheric density at ground level about 1.5 times. Even a person with wings strapped to their arms could fly in an atmosphere like this, so we could have creatures like this.
Hagen bases his ideas on known planets and the evolutionary history of Earth. But it's all pure speculation, until we find life in alien atmospheres.
I would be pretty thrilled just to find microbes under rocks on Mars, for instance. They don't have to walk up and shake hands with me to get my blood up. I would be pretty happy just to know that life has happened twice.
At present, we are alone. Life may have happened just this once. And if it did, then it's only because of our planet's unique atmosphere. As we have soared for miles above the ground, we have journeyed through this ocean of air. The air which shields us, supports us, and sustains us with every breath. Imagine a world frozen solid, encased in ice from pole to pole. No life roams these frozen plains. Only glaciers move across them. This is not some distant planet starved of sunlight. According to a radical theory, this was Earth, 650 million years ago. No one knows what triggered this calamitous freeze. But if it happened once, could it happen again? Imagine the most profound ice age you can think of. Temperatures plummet to below zero, even at the equator. Before long, ice encloses our entire planet. Research suggests that this may have happened not once, but 3 times in our planet's past. Welcome to Snowball Earth.
A snowball Earth is certainly the most extreme climate change we can conceive the Earth having ever experienced.
What would happen if the world froze over today? Massive glaciers creep from the poles, crushing everything in their path.
First of all, the Canadians are going to have to dig much deeper holes when they go ice fishing. Next, the governors of Washington, Idaho, Montana, North Dakota, Minnesota, Michigan, and Maine will probably declare federal emergencies.
Cities grind to a halt. Power lines collapse and water supplies freeze. Cars won't start. Roads are cut off by ice. Buildings strain and crumble under deep drifts of snow. Everything is entombed. Our frail bodies struggle to survive.
I think human society would collapse if a snowball Earth happened again.
The oceans freeze over. Fish die and marine ecosystems collapse. Our food supply becomes exhausted. Any surviving humans are trapped in an icy hell.
We would have a mass die-off of humans simply because we could not grow enough food under these conditions.
Lies in the existence of silicon-based life. Join us on a journey through space and time as we explore these questions. From the possibilities and challenges of interstellar travel to the paradoxes that confound our understanding of the cosmos. This video will take you on an unforgettable adventure into the unknown. Are you ready to discover what lies beyond the stars? The dream of exploring the depths of space beyond our solar system has long captured the imagination of mankind. But is interstellar travel just a distant fantasy, or can we really achieve this goal in the near future? Thanks to the scientific and technological advances made in recent years, we're closer than ever to interstellar travel becoming a reality. The development of new propulsion systems, advances in material science, and our understanding of cosmological theories brings us closer to developing the necessary infrastructure and technology for interstellar missions. However, this ambitious goal has its challenges. The vast distances between stars and the large number of threats lurking in outer space make interstellar travel difficult and potentially dangerous. If we're being optimistic, and certainly not unrealistic, humans will be able to achieve interstellar travel within our lifetime. The possibilities are endless.